Hi, my name is Gracie Guidros, and this is my final project for Geology 1003. The theme of this project is major climate shifts, significant tectonic events, and mass extinction events. In summary, we will be covering the end Ordovician mass extinction, the global glaciation in the late Ordovician period, also known as snowball Earth, the late Devonian extinction, the end Permian extinction, the fragmentation of Pangaea, extreme global warming in the Triassic, the end Triassic extinction, the end Cretaceous extinction, and most importantly, the modern functional extinction of insects. The end Ordovician mass extinction occurred around 443 million years ago, primarily affecting marine life and taking place in shallow seas around ancient continents such as Gondwana. It was triggered by a rapid global cooling event, likely linked to the onset of glaciation and falling sea levels. This extinction wiped out about 85% of marine species, including many trilobites, brachiopods, and graptolites. The event marked a significant shift in biodiversity, favoring species that could survive in colder, shallower environments. Evidence for this extinction includes widespread glacial deposits and isotopic changes indicating global temperature drop and ocean chemistry shifts. This is a graph of solar levels in the Ordovician period, Ordovician, however you pronounce it. So as we can see throughout different parts of this time period, the solar levels stay pretty consistent until there is a drop. Then there is a significant drop in solar levels again. This lack of heat brought on by the sun and solar radiation led to a global cooling event, which led to the extinction of many species and creatures on Earth. The Ordovician mass extinction was triggered by a global cooling event, which is a climate shift, and glaciation likely due to the continental movement towards the South Pole. Sea levels dropped drastically due to ice formation, leading to loss of shallow marine habitats. Over 85% of marine species were wiped out. Then we have the global glaciation that followed, also known as snowball Earth. Late Ordovician global glaciation occurred over Gondwana, which was positioned near the South Pole at the time. It was caused by a combination of decreasing atmospheric CO2 and continental positioning that favored ice sheet formation. This event dramatically cooled the climate, causing sea levels to drop and resulting in widespread marine habitat loss. The glaciation directly contributed to the end Ordovician mass extinction and indirectly impacted ocean circulation and oxygen levels. Geological evidence includes glacial tilites, striated rock surfaces, and oxygen isotope records indicating a sharp temperature drop. In this graph, we can see the CO2 levels during the late Ordovician time period. This is around where the extinction happened, and that is also when the Earth entered a glacial period, also known as snowball Earth. So as you can see, the CO2 levels dropped, and when you have more CO2, it makes it hotter, and when you have less CO2, it makes the Earth cooler. Snowball Earth, aka global glaciation and a climate shift, had Earth nearly or completely covered in ice. These extreme climate changes may have been influenced by tectonic changes and reduced atmospheric CO2. This impacted Earth history in a multitude of ways. Photosynthesis slowed, and ocean chemistry shifted, and this may have paved the way for the Cambrian explosion by triggering evolutionary bottlenecks and new niches. Then we have the late Devonian extinction. The late Devonian extinction was a prolonged series of extinction pulses affecting marine ecosystems, particularly reef-building organisms, and occurred mainly in shallow marine environments. It was likely caused by ocean anoxia, triggered by global cooling, sea level fluctuations, and possibly volcanic activity. This extinction event led to the collapse of reef ecosystems and a decline in jawless fish, altering the trajectory of vertebrate evolution. The extinction also slowed the development of early terrestrial ecosystems by disrupting the marine nutrient cycle. Evidence includes black shale deposits indicating low oxygen levels and a decline in biodiversity in the fossil record. As we enter into the late Devonian, we can see that another extinction occurred due to, yet again, cooling in the climate. This particularly devastated marine species. The ocean became anoxic. The late Devonian extinction included a prolonged cooling, possibly due to expansion of terrestrial plants drawing down CO2, also potentially linked to tectonic uplift and weathering from the Akkadian orogeny. Coral reefs were devastated and marine biodiversity plummeted. Land plants and early vertebrates survived and diversified afterward. Next is the end Permian extinction. The end Permian extinction, famously known as the Great Dying, occurred around 252 million years ago and devastated both marine and terrestrial life. It was triggered by massive volcanic eruptions that released greenhouse gases, causing extreme global warming, ocean acidification, and anoxia. This event wiped out over 90% of marine species and 70% of terrestrial species, reshaping the biosphere. The extinction drastically altered climate and ecosystems, leading to the dominance of new groups in the Triassic. Evidence includes widespread volcanic layers, carbon isotope shifts, and fossil gaps across the Permian-Triassic boundary. In the Permian era, during the end Permian extinction, we can see that there was an increase in CO2 in the atmosphere. The Earth warmed and species began to go extinct, especially because the oceans became acidic. The end Permian extinction was caused by massive volcanism, which released CO2 and methane, triggering extreme global warming and ocean acidification. It's known as the Great Dying. Over 90% of marine species and 70% of terrestrial vertebrates went extinct. This led to major evolutionary restructuring of ecosystems. Following is the fragmentation of Pangaea. Between 300 and 180 million years ago, the prehistoric supercontinent Pangaea reigned supreme until its gradual continental drift broke it apart, forming the 7 continents we know today. Extensive volcanic activity in the Earth's mantle only furthered the fragmentation of Pangaea, rifts and fissures taking precedence over the landscape. This breakup resulted in the formation of new oceans and mountains, changing ocean currents and influencing the evolution of marine life. With rising levels of CO2, global temperatures increased. These factors combining to extinguish 76% of species residing on Earth, named the end Triassic extinction event. As indicated by patterns of seafloor spreading, scientists were able to recognize the existence of Pangaea as well as its deterioration. This is a more detailed graph showing the victims of the end extinction, and also a few survivors, but mainly we are focusing on this increase in CO2. This warming led to oxygen loss. Of course, what was natural for Earth's tectonic plates is that we have continental drift, in which the continents naturally drift apart over time. As this is happening, there is increased volcanic activity beneath the Earth's surface. Magma is allowed to escape from the Earth's mantle, creating further divisions. As seen in this image, 2 plates are moving apart, which is driven by the magma forcing its way out and breaking apart Pangaea. The fragmentation of Pangaea was a tectonic breakup, and it caused new ocean basins, rifting, and volcanism. This altered ocean currents and climate patterns, created geographic isolation which fueled diversification, also likely contributed to the rise of the Atlantic Ocean and changing monsoon systems. Coinciding with the fragmentation of Pangaea was extreme global warming. During the Triassic period, extreme global warming occurred following the end Permian extinction, primarily due to continued volcanic activity and rising atmospheric CO2. This warming accelerated recovery but also led to unstable climates, ocean stratification, and expanded anoxic zones. It allowed new reptile groups and early dinosaurs to emerge while restricting marine diversity in some regions. The warm, dry conditions influenced desert expansion and delayed the recovery of complex ecosystems. Geological evidence includes widespread red beds, evaporites, and high levels of carbon isotopes indicative of greenhouse conditions. In the Triassic period, there was a high level of CO2 due to all of the eruptions that had been happening along with the fragmentation of Pangaea. All of that volcanic activity released more CO2 into the air. This high CO2 led to a higher global temperature, which also led to a climate shift. Here is another graph showing CO2 levels, and this would lead to the end Triassic mass extinction. The extreme global warming in the Triassic was possibly triggered by methane hydrate release or volcanic activity. CO2 levels spikes causing rapid global warming. Ecosystems shifted poleward, and tropical species expanded their ranges, major biotic turnover, and ocean plankton. These two occurrences, the climate shift and tectonic plate shift, led to the end Triassic extinction event. Over 200 million years ago, a global mass extinction occurred, resulting in the demise of about 76% of both marine and terrestrial species. As Pangea began breaking apart, volcanic activity increased, worsening the effects of global warming. Sea levels continued to rise, as well as the acidity of the ocean. The climate had become dry, with volcanic eruptions releasing overwhelming amounts of carbon dioxide into the Earth's atmosphere, effectively wiping out all land animals except for dinosaurs and other groups. Evidence for the occurrence of this event included drastic reduction in species diversity and the disappearance of most vertebrate fauna. Next, we enter into the famous end Cretaceous extinction event. The end Cretaceous extinction occurred 66 million years ago and is most famously linked to a massive asteroid impact near the Yucatan Peninsula, forming the Chicxulub crater. The impact caused rapid climate disruption through firestorms, darkness from atmospheric dust, and a dramatic temperature drop. This event eliminated about 75% of species, including all non-avian dinosaurs and many marine organisms. The extinction paved the way for mammal diversification and reshaped terrestrial and marine ecosystems. Key evidence includes a global iridium layer, shocked quartz, and a sharp boundary in fossil records. Concerning the end of the reign of the dinosaurs, we enter into the end Cretaceous extinction event. As we can see here, the evidence supports a meteorite impact because of the severe temperature drop, meaning that the Earth is cooling. There is a significant temperature drop. Atmospheric dust blocking out the sun, so the Earth was not able to be heated as consistently. As seen in this graph, it was a hectic time because of the sudden temperature drop and then warming soon after. The end Cretaceous extinction was likely caused by an asteroid impact, plus volcanism led to climate chaos, cooling from aerosols and then warming. It impacted Earth's history by ending the reign of the dinosaurs. Mammals and birds diversified in the aftermath. This triggered a cascade of evolutionary shifts in plants as well. Finally, we end with the modern functional extinction of insects. The modern functional extinction of insects is an ongoing global issue observed especially since the 20th century. It is caused by habitat loss, pesticide use, climate change, and pollution, reducing population to levels where ecological roles cannot be fulfilled. This decline threatens pollination, soil health, and food webs, affecting agriculture and biodiversity. Changes within the theme include species collapse, local extinctions, and narrowing ecological niches. Scientific evidence includes long-term population studies, biodiversity surveys, and ecosystem impact models. So, according to this chart, insects are in global decline. This graph also shows the decline of insect species. All of these insects are threatened and also endangered. Especially flies are in the decline. When you compare this to land mammals, birds, vertebrates, amphibians, and reptiles, insects are in a much larger decline than these groups, showing a functional extinction happening right in front of our eyes. The modern functional extinction of insects, which is ongoing, is driven by modern climate change, habitat loss, pollution, and pesticide use. It's a mass extinction still in progress. This will heavily impact Earth's history. The threats of ecosystem collapse are imminent. Pollination, nutrient cycling, and food webs are all at risk. This ongoing extinction could rival past extinction events if these trends continue.